I'm Drew Thorstensen, one of the engineers integrating power systems into IBM Cloud's VPC, or Virtual Private Cloud solution. Today I'm going to show you how to boot your first power-based virtual server in the IBM Cloud. But before I do that, let's talk about some prerequisites to get started. When you get started, you need a cloud.ibm.com upgraded account. If you're creating a new account, usually there are some promotions available to you. I've already logged in on this tab, and when you log in, you'll just land at cloud.ibm.com. From here, you can open up the menu bar on the left-hand side, and we can scroll down to the VPC infrastructure. Before we dive into this, let's start with a bit of background on what a virtual private cloud, or VPC, is. The VPC construct is the ability to create your own private cloud on public cloud infrastructure. This may sound a bit odd, but essentially you're creating your own lockdown space in the cloud where you can define your own security constructs about who can and cannot access that cloud infrastructure. The power integration is built on the Gen 2 compute platform. This should load by default when you click into the VPC infrastructure, and you can verify that you're on Gen 2 by looking at the top left panel. The first thing that you need to create is your own virtual private cloud. To do this, you can click the button here or the VPC's button on the left panel here. As you can see, I've already created a few virtual private clouds. However, creating a new one's fairly easy. You simply need to give it a name, define some access controls. If you're unsure what to put, just use the defaults. And you need at least one subnet. The subnet defines the region that you're within. A region has at least 3 zones available to it. You would use the zones to create a highly available application. Or if you're just looking to spin up a VM, you can just pick one of the zones and deploy to that. You also can attach an IP address range to this subnet, and the public gateway feature would allow your VMs to be able to talk to the public internet through a router. Since I already have a VPC created, I can move forward here. The next thing you need to do is to upload a public SSH key. As you can see, we've got several in the service already. And the SSH key is very important because the images that we deploy do not have passwords associated with them. The SSH key is how you get into your VM. You maintain your own private key, you upload the public key to the cloud as part of the provisioning process. Next up is provisioning your own virtual servers. To get started here, you simply click the virtual server instances, and then you can see that I have a few instances already created. If I hover over the profile, you can see a bit of information about them. One question I often get is whether or not the power and the x86 resources are on the same networks. They absolutely are. You can share within a given subnet x86 and power resources. All of the capabilities over here, such as access control lists, security groups, VPNs, or load balancers, apply homogeneously between the x86 and the power VSIs. A given security group, for instance, can be applied to both x86 and power resources. When you want to create a new instance, just click the button here. A new instance has several fields, but again, you can generally select the defaults. I will pick the VPC I wish to deploy in. And if I scroll down, you can see the processor architecture. Selecting power is simply a radio button, and when you do this, the operating system list is updated. You'll also notice that the profiles below get updated if I flip between the two. you can see that the balance profile on x86 starts with 2 vCPUs, 8 gigs of memory, 4 gigabits of network bandwidth. The power is similar with 2 vCPUs, 8 gigs of memory, and 6 gigabits of network bandwidth. If I select Ubuntu Linux, the GPU options also become available on the power nodes. And if I want to select a wide variety of different profiles of different sizes, I simply click this All Profiles, and I get balanced compute, memory, and GPU optimized instances. Next up, I'll pick my SSH key pair. That's the default one. And then I can attach any data volumes or additional network interfaces I may want applied here. After that, I simply create the virtual server. The VSI creation takes a few seconds to boot, maybe 20 or so. You can spin up thousands of VSIs in parallel in very short order. It is a highly distributed solution. Now, you'll also note that the IP address that it assigns is a 10-dot private IP address. I cannot get to that IP address. That is on a private network within my virtual private cloud. However, I want to access that VM so that I can SSH to it. So in order to do that, I'm going to assign a floating IP. Now, this IP should be available. The instance is powered on. And if I ping it, we can see that it is responding. If I SSH to it, we can see that this is a Ubuntu instance. Now, a couple things here regarding how it is a power-based instance. You can see that here because it says PPC 64LE. But a little bit about that. If I run the following command here, we can see that it is 2 vCPUs, so 2 threads available to it. Now, the host, or the VSI that boots, when you buy a vCPU maps to a thread. Power cores, however, have SMT4. By default, we boot into SMT2 mode. That means 2 threads per physical core. 2 vCPUs gives you a full core. However, since the power nodes have 4 physical threads available to it, you can take advantage of that by running the SMT command, the PPC64 CPU SMT command, to bump up to 4 threads. And that doubles the cores per thread. So now I have all 4 threads available on this instance. By default, we boot into SMT2 mode for compatibility reasons. There's a fair amount of software that's built on 2 threads per physical core. If you were to order a 4 vCPU VSI, you'd actually end up with 0, 1, and then 3 and 4. However, you could change that into SMT4 mode as well. Now, booting up to SMT4 also gives you a nice boost to throughput on your system. Another thing to note here is that this PPC64 command can also show you the frequency of the underlying system, which is 3.7-ish gigahertz. Now, even though this is a Power 9 system, it is, of course, a Linux OS. This VM is booted into Ubuntu, so installing any software is just as you'd expect. For instance, I can run my apt-get update command. Notice that it uses the internal mirrors to provide those updates. And next up, I can install some software, for instance, MariaDB or MongoDB or OpenJDK 11 or Nginx or Node or Python or even Erlang. You can see that's a lot of software to install, but the point being that that software is available off your mirrors, able to install on your system, ready to go. And that gives you an idea of what is available to you on these power-based instances: the 4 threads per core, the increase in network bandwidth, and the common API and user interface to deploy these power instances right alongside your x86. Thank you for your time. We hope you enjoy the solution.